Okay, so let's talk about the integrated direct laser sublimation unit for the NanoFrazor. I'll show you why we developed this, how it looks like, what it can achieve, and in the end, how do we plan to continue. So if you have seen some of our previous webinars, you know that the NanoFrazor has an ultra-sharp heatable tip that can be heated up to 1300 Celsius and has diameter at the apex that can be down to 4 nanometer. This tip can be used for patterning, like you can see here, and in-situ imaging, as you can see here. This allows for 3D patterning because we can control the depth at which we push our tip, and then with in-situ metrology we can check how the patterning is going and adapt the patterning parameter to match the target topography. The NanoFrazor can also write with very high resolution due to the very small size of the tip. Since we can image what you have on the surface and write with the same tip, we can do what we call markerless overlay. Moreover, since we are not bombarding the substrate with the high energy particles, we do not damage any sensible material that might be on the surface. And here on the right, you can see the NanoFrazor Explore and its specifications. So this is really good to do what you can see here at the left. So it is very high resolution structures, very accurate overlay, and 3D structures with unprecedented vertical resolution. The NanoFrazor is also really good to do what you can see in this image here at the bottom left. This image comes from a publication from Xiaori Zhen from Elisa's Redos group in New York, and it is an example of overlay and low damage of sensible materials. So here basically they had a flake of 2D material which was buried under the resin stack. With the NanoFrazor they could image it, see the flake and pattern the electrodes on top of it. Not only this central part of the device was fabricated with the NanoFrazor, but the whole device was made with the NanoFrazor. This is a very good example for us because it shows how really with the NanoFrazor you can do everything. Xiaori said that it was taking him 10 minutes to fabricate each of these contact pads, which is very impressive if you think that this is a scanning probe technology. But I'm sure he wanted to do it even faster. The idea that we had for a long time to help our users to fabricate device faster was to integrate the laser writing system inside the NanoFrazor, which could have been used to write this lower resolution big area of devices. So the first prototype of a direct laser sublimation system integrated with the thermal scanning probe lithography was done in collaboration with the IBM in the IBM research labs here in Zurich. You can see the picture here on the left. And it was shown that this laser could directly evaporate PPA, and so it could integrate very well with the thermal scanning probe lithography technology. The first device fabricated with this prototype was a single electron transistor, actually two of them, you can see in this image here. This was made, was part of a European project. The part inside this red rectangle here was written with laser, except these two smaller insets, which contain the higher resolution part, which were written with the thermal scanning probe lithography. And here you can see a zoom in an FM image after etching of those areas. So it was possible to make channels of less than 25 nanometer that after some oxidation could produce a single electron transistor. In 2018, Swiss Litho joined forces with the Heidelberg instrument. So now the NanoFrazor is part of a bigger family of direct writing system, and all the others are laser writing systems. So actually the idea of developing this direct laser sublimation unit for the NanoFrazor became really concrete. And the vision was of combining the high resolution of thermal scanning probe lithography with the high throughput of the laser writing system. So here I just put next to each other the NanoFrazor and one of the laser writing systems from Heidelberg, the DWL 2000 or 4000. And this would be a combination of these two would be a really nice tool with the NanoFrazor resolution and the laser writing system throughput. But this is not as simple as it might look like. So we cannot just put a small laser writing system inside the NanoFrazor as it is. and we cannot just put the NanoFrazor inside the laser writing system. This is because the two technologies have quite different working principles. The NanoFrazor with the heated tip directly removes the resist, so there is no development needed. In a laser writing system, you first expose the resist, and only afterwards, with the development, you remove it. Also, the resist that we can use in the NanoFrazor is the PPA, at least most of the time, which is optimized only for thermal scanning probe lithography. Actually, it's quite insensible to light, it's transparent basically. Instead, the resist used in the laser writing system are very well optimized for light, with a very high sensitivity. But on the other side, if you try to push a heated tip into them, they make it quite dirty. So what we decided to start from is to build a unit similar to the prototype which was developed in collaboration for IBM for a direct laser sublimation of the PPA into the NanoFrazor. In this way, we have a tool that can do the high resolution patterning with the tip and can also do the in-situ metrology and imaging, and can write the micrometer size structures with the laser. So, and these can have a throughput that is supposed to be 100 times higher than the tip. Of course, we keep having the reading capability of the NanoFrazor, so we can do the metrology, as I said before. We can do the overlay and stitching. And since we have this cantilever inside the machine, we can do some precise compensation of tilting of the substrate, and we can do some compensation of drifts of the system and better focusing, and so on. Okay, so now let's see how this unit looks like. The optical design was made by our colleagues in Heidelberg. Here you can see a drawing. There is a LED for the illumination on the back, a coupler here for the fiber bringing the laser light. On the other side there is a camera, so we can produce an image, field of view is around 1 millimeter to 1 millimeter in the NanoFrazor software. And then there are mirrors to reflect the beam to the objective, which is here. This is a front view of the laser writing add-on on top of the NanoFrazor. So this on top is the laser optics, whose drawing was shown before. And this is the substrate here. And we focus the laser beam on the substrate around a few hundred micrometer in front of the tip, which is also here. So the laser that we use is a continuous wave 400 nanometer laser with a max power of 300 milliwatts. The numerical aperture of the objective is 0.3, and we obtain a beam waste of 1 micron. We also have an autofocus function, so the laser is focused automatically on the surface. There is an automatic estimation of the tip to laser spot offset, so that it's easier to align structure written with the laser to structure written with the tip, and vice versa. And then the system, of course, comes with all the laser safety interlocks that you need for safe operation. Okay, now let's see what this system can achieve. First, we did some exposure tests. So we're writing with the laser and then analyzed what we wrote with the imaging capability of the NanoFrazor. You can see the NanoFrazor image here on the bottom left. So in the left part, we fix the time, the exposure time, and change the power. Here you can see the powers in milliwatts. We always wrote a line, which is only a marker, where there are a lot of pixels next to each other, so we always write something, and then a dot next to the line, which is our measure. As you can see, at lower power, we don't write anything. As we move up at higher power, we start writing, and we write deeper and deeper. We did a similar experiment by keeping a fixed power and changing the exposure time. Here on the right, you can see the results of this test. And we have the depth plot versus the laser image, which is nothing else than the power times the time. As you can see, we can have some control on the depth at which we write. Another interesting point is that the patterning doesn't start at 0 energy. We need to overcome a certain dose before the patterning starts. Now, let's see, we test the resolution, yes. So when we designed the system, we had in mind a resolution of 1 micron, and this is what we specify. And this resolution can really be easily achieved. Once the system is decently focused, you just start writing and you always write better than 1 micron. We try to push the resolution by optimizing the parameter, and we could achieve what is shown here. It's like 400 nanometer lines and spacing. For the moment, this is the best result we had with our machine. We also try to see single dots, how big they are. You can see here in the zoom AFM image, they end up having a diameter of around 200 nanometers. So actually it's smaller than the beam waist. And this is, we think, is due to we call it non-linearity of the pattern. So we need to overcome a certain dose before we start patterning. And because of the shape of the beam, the higher dose in the middle. This non-linearity in the patterning produces an effect that is a kind of proximity effect that you can see in this image here at the top. So here we made a few exposures at different distances from each other, like single dots. As you can see, as long as the pixels are more than 800 nanometer away from each other, they are independent, so their depth doesn't change as a function of distance. When they get closer, they start to merge, and they end up producing a dot which is much bigger than the 2 dots when they are far away from each other. To better understand what was going on, we tried to make a second exposure in the same place, and you can see the result here. Now with the second exposure, we see that also in the kind of isolated dots, so the one which were quite far away from each other, we remove much more material than the one we removed with the first exposure. So what we conclude is that the first exposure caused some kind of non-volatile modification of the PPA, which allows the second exposure to be much more efficient. In a way, we think we need to activate the PPA before we can remove it to the laser. Another effect that we observed is that the interference between the lights that gets scattered at the interface between the various layers in the substrate can modify the efficiency of the patterning. Actually, if you have destructive interference in the PPA, you have very difficult patterning. If you have constructive interference, you have much easier patterning. Here you can see a calculation of the amount of energy that we expect to be dissipated in the PPA as a function of the thickness of the layer of lift-off resist under the PPA. As you can see, we expect maximas at around 40 nanometer, minimas at around 100 nanometer, and then this will repeat. We made some experiments to check if this is true, and actually we confirmed this prediction. You can see this in the image here below. So where we plot the energy that is needed to achieve the 30 nanometer deep patterning in PPA, so complete removal of the PPA, versus the PFGI layer thickness, so the thickness of the lift-off resist stack layer. As you can see, around these thicknesses we need much lower energy as expected than at this thickness here, this 100 nanometer, which corresponds to the minimum of the energy which should be dissipated in the PPA. As we increase again the energy to 150, as we increase again the thickness of the PNGI layer to 150 nanometer, we go to the next maximum, and again we need little energy to evaporate completely the PPA. Okay, now let's see a demonstration. So here I was just patterning one of these Heidelberg logo here. I load the design and start patterning. Here you can see the laser light on and the sample moving fast under the laser, and then the patterning is done. This is around 40 micron times 40 micron, and was done just in a few seconds. So after patterning this logo, I went at the same spot with the tip and imaged it. You can see here the AFM image obtained with the NanoFrazor. You can see actually the single pixels of the laser here because I was using quite a big pixel size. And then to show that we can write in the same tool with the tip and with the laser, I decided to write like a small Heidelberg instrument logo here below the big H. And here you can see a zoomed in image of this logo. This was written in the tip, and here you can see a further zoom. So now this shows that we can, in the same tool, write the sub 100 nanometer resolution features, actually 25 nanometer half pitch with the tip, and we can write the coarser structures with the around 1 micron resolution or even a bit less with the laser. Okay, now finally let's see one more realistic example. This is a dummy device, is 500 micrometers times 500 micrometers, and it was written with a laser, and it took just a few minutes. This is just to repeat once more how the laser increased the throughput of the NanoFrazor for the low resolution part, and of course you still have all the features of the NanoFrazor for the high resolution part of your device. So now we are at the conclusions. I will show you our direct laser sublimation unit for the NanoFrazor. Actually now every NanoFrazor Explore has this unit by default. This gives higher throughput for the micro features and preserve the tip for where it's needed. So the high resolution, the 3D, precise stitching and overlay, and low damage patterning. Of course, we still have a lot of ideas of how I want to go on with the laser. One idea is that we want to see how well we can control the 3D patterning with the laser. Another very interesting idea is that actually we're already working on this. We want to increase the PPA photosensitivity with the use of photoacid generators. This looks quite promising, and it would be really cool if we could achieve a sensitivity equal to the one of the standard laser writing resist, because then we could increase the throughput of our laser a lot and really make achieve the initial vision. So I have a tool which has the full throughput of the most advanced laser writing system and the resolution of thermal scanning probe lithography.